Hello, we're back for the next episode of the Science of Energy, and what we're doing in this recording today is trying to clarify a few points and actually to get a little bit more specific because so far we've been talking about energy and work and heat, and we've been explaining it, or I've been explaining it to you, and hopefully it's making sense. But it's now time to get a little bit stricter in how we're talking about these things, in some of the symbols that we use, conventions, the way we discuss it, so that we start moving towards a more rigorous understanding. And if you think where we started off with this very broad general statement that energy is about the ability to cause change. And I've been sort of making fun of this definition the whole long way along because it captures something important, but it's hardly adequate, isn't it? And then we tried to start fleshing out more about it by looking at the five major types of energy that are important. And hopefully that's starting to become clear in your mind: thermal, mechanical, electrical, chemical, and nuclear, all right? And we've made the claim that really, a claim that I'm going to justify, that these five types of energy can be explained with a common set of basic concepts and ideas and even a common set of equations, all right? And I also explained the distinction between classical thermodynamics and statistical thermodynamics. We are right now in the middle of classical thermodynamics. The way I'm talking to you, the way I'm describing things to you, is the classical approach. And as we start with all these really simple examples, we go, oh, well, imagine you have this cup of coffee been cooling down, and these really simple constructs. And what's remarkable about these very simple constructs is that they are incredibly powerful in explaining some very profound things. You'll notice soon we'll start talking about pistons moving up and down. And if you pick up any book about thermodynamics and energy, you see a piston, a picture of a piston. And I think we can. I'm pretty sure Carnot's the person that started that idea. And you initially think, why are they talking about a piston? And then as you look at it further, you realize, this is a very good choice because a lot of very important factors about basic behavior of work and heat and energy and all these good quantities that we're talking about are shown through this example of a piston moving up and down. Anyway, statistical thermodynamics is very different, and we're not starting on that yet. We'll talk about that at some stage. The moment we're really talking about classical thermodynamics. So that's the first things that we were really talking about. I think the second thing is we started to get into the whole idea of what work and heat is. And I went through at some length trying to explain to you that the best way of understanding work, we start off with mechanical work, is that it's really about a force being applied to something through a distance. All right. And we used the example of dragging the coffee cup across the table. We then talked about the idea of pushing up against gravity, another great example. And these examples could keep going on. And can I stress to you, we haven't gone through all these examples, but you can construct the same sorts of arguments with electrical energy, chemical energy, nuclear energy. Nuclear energy is a bit more complicated, but you can construct the same basic kind of arguments. And so this generalized version of what work is, which is an important thing to sort of establish as a building block to establishing thermodynamics, led to this sort of definition of energy, which is, well, force times a distance, right? That concept. And force has the units of Newton, and we're talking metric units, and distance has the units of meters, right? And so we come up with this basic unit of energy, which is uh, force times distance. And in honor of Joule, who did a great deal to establish the nature of this, we call that the Joule. So you're doing very well when you have a unit named after yourself. I think I'd be very, very happy if a unit was named after me. I have a feeling it might be something fairly trivial, like how many times I repeat a word in a lecture or something. But Joule, he did some great work, and we named the unit Joule after him. And there are other units. There are calories, for example. There are British thermal units. There are a number of units associated with different unit systems. I'm going to talk in the metric units, not because I've got some problem with imperial units as such, but it's just simple at this stage to describe these things. So we're going to use those metric units to discuss these basic ideas. Then we talked at some length about this incredible experiment, a series of experiments actually, by Joule. And Joule was trying to show the equivalence between, work and heat. And he had this great idea of you get a weight, you suspend it over a pulley. This pulley is turning around a turbine in a small tank or glass, and this is very well insulated. This tank and all the joins are very well lubricated, so everything's working as as best close to ideal as possible. And as this weight falls, it turns the spindle, and the spindle, the paddle on the end of the spindle, experiences friction from the liquid, and that friction causes heating up of the liquid, and that then leads to a temperature rise, which Joule was very his various technical people he worked with were very good at measuring, and they could equate a quantity of energy with a quantity of work. A quantity of heat with a quantity of work. So this was a profound experiment. And when I finished explaining this at the last lecture, we're very, very close to just expressing the first law of thermodynamics. In fact, there's a temptation just to jump in and tell you the first law of thermodynamics because it's so close. But I feel that there's a few underlying aspects of thermodynamics as a science that we need to go through that will avoid confusion later. And please, please remember that as I'm describing these things to you, at times I'm being a bit colloquial. I'm using just sort of everyday language, and sometimes everyday language is not precise enough for what we're talking about. So I'm going to get a little bit more precise, a little bit less colloquial, and actually, get down to some of the strict definitions and conventions that are used. Now, why are we doing this? Because I'm trying to bore you, or because I'm trying to be a real hard ass about them? No, it's to avoid confusion about what we're saying. And this business about work and heat and energy is a good example of that. And I want to clarify a few points about what's been said so far so that we can make sense of the next bit, which is when we really get into this issue of what the first law of thermodynamics is. Um, some people think they understand thermodynamics, or they say they understand thermodynamics, but when you look closely at it, what they do is they have a kind of sort of pop version of it that is actually has misunderstandings in it. So I'm trying to avoid that. I don't want to bury you with details, but I also want to make sure that you appreciate some of these important definitions and conventions, which are quite important to the understanding of how energy behaves. All right, so let's talk through one of them. The first thing is in thermodynamics, we talk about systems and boundaries. We do that so to avoid confusion about what point are we saying this the system we're describing, where's its boundary when we're talking about energy leaving or work being done by that system or work being done on that system. Whereabouts are precisely are we talking about? Actually, this is a really important issue at the moment with the accounting of CO2. So people are all the time trying to understand how much CO2 is generated by a particular process, right? Either industrial process or the motor in the engine, whatever that system that we're studying is. And the where you draw the boundary is incredibly important because what often happens is that there are things outside the boundary which generate a lot of CO2. So if you draw the boundary at a particular place, you can make your system look like it's not causing much CO2, but actually it's not a full picture. So this issue of drawing boundaries at the right place of a system is very important when you're trying to analyze energy, and also when you're trying to analyze the resulting pollutants from processes. So when we start off is we'll start off with this very simple one. I'll start once again with the famous coffee cup. Coffee cup is always useful, and a coffee cup we can look on as some sort of process or some sort of system. All right. So at this point, I don't think we need to worry about whether it's a process or a system. I'll use the word system. It's a system. It's a cup. It's a system. So we draw a boundary at some point around it, right? It might be the perimeter of the cup, or it may just be a small distance around the cup. And we say, this is the system that we're analyzing. So with this system in thermodynamics, we're particularly interested in understanding whether the mass inside the system is flowing in or out, right? Or is it leaving, partially leaving? Is it changing, right? And the other one is we're interested in the energy, the overall energy of the system. Is there energy flowing in and out of the system? So in the situation where energy can flow in and out from a system, but the mass cannot, we call that a closed system. That's the convention. We describe that as a closed system. In the case of a system where the mass and the energy can both flow in and out freely, we call that an open system. All right. And there are large differences in the behavior of closed and open systems. So you'll start seeing this term. So just remember, a closed system, energy can go back and forth across the boundary, but the mass is staying there. All right. In the case of a open system, the mass and the energy can flow out of the system. All right. So that's an important distinction. When you have a system where the mass and energy cannot flow anywhere, they're just stuck inside the system. In other words, that coffee cup, the energy is not going anywhere. There's no heat coming out of it. It's completely insulated within the system. And there's no chance of me drinking the cup of coffee. The coffee's staying there, right? It's not evaporating. I'm not drinking it. It's going nowhere. The mass is going on there and the heat's going nowhere. We call that an isolated system, all right? So that's a very particular case, an isolated system. There are a few finesses to these basic definitions. I've one example would be you can have a closed system that's got a moving boundary, and I've picked an example here where you've got a flame underneath a piston. We're starting to bring the piston in. You're going to see a few pistons. Get used to the piston. So if you put a gas into a piston, and that piston can move up and down freely, depending on any pressure that it feels. If it's got some volume of gas in there and I put a flame underneath, the gas will expand and the piston will move up. All right. And that's the example of a moving boundary, even though it's a closed system. The gas inside the piston is not going anywhere, right? But it is expanding and it's causing this piston to move. So we call that an example of a closed system with a moving boundary. And there are other variations. All right, that's okay. At the moment, just to get a sense of an open system, a closed system, and a moving boundary system. And look, when I'm talking about some of these things in the following lectures, I will, yeah, remind you of some of those basic definitions so we don't get ourselves confused, because it can be confusing. Now, the other thing I want to talk about is the whole convention around the direction of work and heat. Now, even though I have been studying thermodynamics since, I'm trying to remember, this could be embarrassing. I've been probably first started studying thermodynamics, well, well over 40 years ago. So this is quite some time ago. And I've been working in thermodynamics most of my career. I still have to stop and think about this, all right? So don't get worried if you go, oh God, I get a headache when I'm about to describe to you. This convention is not intellectually important. It's just something to understand that you need to have a convention. Otherwise, you will confuse yourself. See, one of the things that we're doing in the science of energy, thermodynamics, is we are trying to make sense, quantify with quantifiable, amounts, what sort of energy and work and heat is changing in a system. All right. And so to do that, we have to be able to get these sums correct, and these sums need to have a convention. All right, it's really a convention. So basically, the basic convention is that if heat is going into a system, we call that a positive. The Q is positive. If heat is leaving the system, it's negative. And I always remember that one easily because what's very common, you may remember that I told you that my first love is chemical thermodynamics. And in chemical thermodynamics, you have reactions that generate heat, like combustion. And when you have combustion, you always have the heat term being negative. Right? So that's the way it stays in my mind. Right? Now, with work, it's the following. It's a different convention. If you're putting work in, we call that a negative. It has a negative quantity associated with it. And if we have work going out from the system, so the system is generating work somewhere, it's a positive. All right. So we've got this sign convention. Don't lose sleep about it. The way I've always thought about it, work and heat are going the other way around. Combustion reactions give off heat, and it's a negative, and that allows me to work it out. That's why I remember it. It's a convention, and I just want you to be aware of it. Now, at this stage, we have been talking about work and heat and energy in a kind of interchangeable way. And I'm sure there's some people who understand thermodynamics quite well who've been watching thinking, oh, he's been a bit lazy with that. And I have been a little bit lazy with it. I've been lazy not to cause confusion, but just to allow the discussion to propel along. So let's now get a little bit more precise about some of these things. All right. So the first thing I want to tell you is that we've come to understand heat and work as boundary phenomena. So at the boundary of a system, you see evidence of heat and work. All right. And that boundary phenomena is not the same as understanding the energy of the system. In fact, systems possess energy, not work and heat. Really, a system possesses energy, and that energy can manifest itself at the boundary at work and heat. All right. Now you may say, oh, that's a funny, why are we doing that? You'll see. Just persevere a little bit. There is some deep thinking behind that definitional issue I've brought up with you. The next one is work and heat are associated with processes, not states of matter. Now, that is quite a profound statement, and I need to explain it to you. So, we can have, say, a gas of water, some water vapor, and that water vapor could be at a certain pressure and a certain temperature. We can say in thermodynamics that the energy of that, which we'll call the internal energy, which we'll talk about more, is unique to that water vapor at that temperature and that pressure. And it doesn't matter where in the universe that water is, that water vapor, at that temperature and that pressure, it has that energy associated with it. All right. And that is independent of how it gets there or how it's made, whether it came from my coffee cup, whether it came from a boiler, a rocket engine. It's independent of the route that it has arrived at that temperature and pressure. That energy is independent. That is a state function. It is a function of its state, not of the process that it's got there. Here's another way of thinking about it. All right. If I get a can of petrol and I'm going to use that in my car, if we analyze how much energy that can of petrol can generate, it is a given set of energy. It doesn't matter where we are, well, as long as we're at the same temperature and pressure. In principle, wherever we are, that can of petrol, that temperature and pressure will give us a certain amount of energy upon combustion, and that energy is available to do work and generate heat. The amount of work and heat generated by that can of petrol depends on the details of the car engine, the exhaust system, the radiator, the air conditioning, etc., etc. And this is very complex, and that is path dependent. That's dependent on the process, where the actual lump of energy available is not. So work and heat are processes. They're part of a process. And they're a process that manifests itself at the boundary of the systems that we're analyzing. And this then comes to this other definition, which is work and heat, because I'm really restating the same idea, actually. Work and heat are path functions. They are not state functions. In other words, they depend on the route at how they've got there, not on just the definition of their states. So, in the science of energy, we will be making a very big distinction between state functions and path functions. And we've been talking last last couple of lectures on these path functions, work and heat, and you will see that this distinction is important. All right. Well, I've gone through some definitions and I've gone to some trouble to define a few points, and hopefully I haven't driven you away with boredom. And soon the next time we talk, we're going to be speaking about a very important state function, which is called internal energy. And we're really, 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 really close to a statement then of the first law of thermodynamics. Thank you for listening. I'm looking forward to describing the next part of this amazing science to you.